Now we've highlighted the centrality of a finding, more than a finding, a theorem, more than a theorem, a proven theorem, robust yet fragile. Dates roughly around 23 years ago. The risks of brittle collapse in the face of surprising challenges is omnipresent for all systems at all layers and scales. No matter what. It isn't solved by adding more automation, because the automation you design, whatever level of autonomy you've been able to develop, whatever technology you've used, still has limits, right? And there are still surprises or challenges that happen at those boundaries. So they are subject to brittleness. The brittleness constraint is universal on all systems at all scales. So this comes from two places. One, as a formal proven theorem circa 2000. Right? This comes originally from Gene Carlson and John Doyle. And there's a series of papers with other colleagues of John Doyle, right, that play out this theorem and the constraint it brings. We will explain this in detail because robust yet fragile drives much of the development, the concepts, and the pragmatic techniques that go on in resilience engineering. But it's not simply a theorem, right? It's actually a general empirical pattern, right? In roughly the same time period, right, in the early 2000s, myself and others were collating, Richard Cook and others, collating empirical patterns from how safety is created and breaks in complex systems across many risky worlds. Again, transportation, disaster response, space, aviation, medicine, wide varieties of studies by many colleagues. And we began to realize circa 2000 that the key difference, the key issue was systems fail, or failure is due to brittle systems, not erratic or unreliable components, including people. Yes, components can be limited. Remember, resources are finite. There are always multiple trade-offs. In design, given finite resources, given limited knowledge, given the power of what you're developing will produce change because it will stimulate others to adapt. All that means there's uncertainty about what will actually play out in the future as you deploy new capabilities. But we do understand in those that the risks of brittle collapse apply no matter what. Now, the empirical findings on adapting to cope with complexity correlated with robust yet fragile in the 2003-2006 timeframe. And this continues to provide a critical linchpin, a kind of an anchor underneath many of the developments that have followed since. Now, let's quote Gene Carlson and John Doyle in 2000. Robust yet fragile means, right, systems which are robust to perturbations they were designed to handle, yet fragile to unexpected perturbations and design flaws. In other words, they are highly competent when events fall within the envelopes of designed for uncertainties and variabilities, but they experience sudden large failures in the face of events that challenge or go beyond the boundaries of that envelope. Again, biology and evolution is highly sensitive to this. Wants competent but not brittle systems. So something extra is needed, right? And we'll refer to that as extensibility, in particular as the discovery of graceful extensibility as a fundamental parameter of all adaptive systems at all scales. So this emerges from another 20 years of previous research or even longer, coalesces around 2000. We pull out these empirical patterns. I meet John Doyle. We start to integrate the line of work he and his colleagues had been doing, what I and my colleagues had been doing, and we start to see a convergence, right? That's adaptive systems at all scales have these extra capabilities to offset the risks from brittleness, right, relative to robust yet fragile.
So progress has come from questions that arise given the trade-off captured in robust yet fragile and the empirical studies, the sort of RYF plus. The pursuit of optimality now increases brittleness. Oh, wait. Brittleness or fragility. What is that? So brittleness is fundamental, and it's a fundamental omnipresent risk for all systems at all scales. Now, what is it again? Brittleness is a characteristic of a system when it reaches the boundaries of its performance envelope. That is, how rapidly does a system's performance decline when events push it near or beyond its boundary. Brittle systems experience rapid performance degradation or collapses or failures when events challenge system boundaries. There's always boundaries. Universal constraints of finite resources, the inherent variability of its environment in a continuous changing world, and because systems operate in a larger network of other adaptive entities. Right? They're pursuing advantage from their perspective for their goals. So each system has an envelope within which it is capable of competent performance. Because competence envelopes are bounded, a core question for all systems is, how does it perform when events push it near or beyond the edge of its envelope? Now, classically, the view has been, well, systems can be operated in a way that it stays away from its boundaries. But robust yet fragile points out that this is not possible. Why? Well, first, we simply empirically find breakdowns in your brain. Breakdowns representative of the risk of brittle collapse are occurring regularly in many, many sectors. You should be tracking them as they occur every week, every month. The ones we lay out this month, right, will be replaced by new ones in this sector or that sector at one scale or another. There's a regular stream of these happening out there. When a system is unable to stretch when challenges arise in the boundary regions, when they are slow and stale to adapt, the risk of brittle collapse rises. With the right forms of adaptive capacity, systems have capabilities to anticipate bottlenecks ahead, to synchronize activities across roles and layers for mutual assistance as stressors on the system grow. They possess a readiness to respond, to reconfigure and reprioritize activities to meet the challenges. In other words, robust yet fragile isn't leaving us stuck with brittleness as a risk. Okay? It highlights another form of capability, form of adaptive capacity that we need to mitigate the risk of brittle collapse. And that's demonstrated over and over again in successful systems, whether that's in the biological realm, the social systems that people like Ostrom studied, the mathematical formalisms that can be developed to show how we can dynamically control in the face of change, right? And in the ways that we can guide systems to operate more safely despite complexities and other pressures.
Now, we've mentioned as fundamental to the development of the foundations for resilience engineering of the finding called robust yet fragile. What does that mean? All right, robust yet fragile says that, hey, let's develop, design, improve a system, some sector, some scale. We want it to be more optimal on certain criteria. We want to make it work better, right? That's part of growth. It's part of seeking opportunity. We want to improve. So we can have increases in optimality on some criteria. However, there's a difficulty. Only pursuing optimality on some criteria leaves us vulnerable to breakdowns due to challenges that arise. We should do more than just pursue optimality. We need some defensive measures. So you think of the pursuit of optimality, emphasize pursuit or pressure for optimality, right? is trying to think of that as kind of an offense in a sports analogy. We can think of, right, how to be robust in the face of challenge as a defensive strategy. Wait a minute, we need to pursue these criteria and achieve more, but we also have to guard against, right, degradations due to challenges that arise. So robustness means I can add robustness checks on my pursuit of optimality. That works if I understand the kinds of disturbances that arise. If they are well modeled, I can design in robustness checks, right, that will offset the occurrence of those disturbances at whatever frequency or distribution those can arise. If I understand them, I can build what may be effective defenses so I can pursue optimality with some additional robustness. It sounds great. We can do this. There are textbooks on how to do this at certain scales, right? Robust control has textbooks. So we pursue optimality and we add in robustness checks, assuming that we understand the disruptions or disturbances that can arise. What does robust yet fragile say? Empirically and formally, it says that's insufficient. It's insufficient, right? Why? Because the system will still be brittle. It will have fragilities. And we'll talk more about how that arises, where that comes from. Again, using the empirical patterns, talking about them in different sectors, and referring back to that these are formal fundamental results. So optimality, forms of optimality, robustness, good thing to do, but there are hard limits on how much robustness you can add to your pursuit of optimality. So you need something more to offset brittleness, right? We're going to talk about that again as extensibility or graceful extensibility. So we end up with a trio that guides the design of all systems because they're adaptive systems at all scales, right? Yes, we should pursue optimality. Yes, we need to add in ways to offset challenge when we well understand those challenges, robustness. And third, we have to design in extensibility, right? Mechanisms that allow us to extend or stretch at the boundaries when surprise goes beyond what we had planned on for disturbances and variations. We need all three. What's the difficulty? Oh, we can add those together. Oh, no, we can't, right? They are non-linearly related. Right? And the pursuit of optimality can sometimes be done in a way that undermines the extensibility. So this is what we will explore in these interactions. What's that? Robust yet fragile is one of the fundamental trade-offs. It's only one of the fundamental trade-offs, though. But it's key to the development of the ideas. We will run through some of the other fundamental trade-offs that constrain the way that we can handle challenge while seeking opportunity.